Aydin Sezgin. This is a joint work with my PhD students, Shuli and Marjam Buluri and Erot Yosvik, who's one of the organizers here. So let's get started. So here's an overview of my talk. So I'm first going to provide the motivation why reconfigurable arrays might be useful, in particular when we look at physical layer security. I'm going to apply those concepts to a particular system model where we benefit a lot, basically. This is going to be a millimeter wave and terahertz in particular. I'm going to, within this context, I'm going to show you two algorithms. The benefits and the disadvantages, and then hopefully with some simulation results, I will convince you that this might be a good idea. Okay, and then I'm going to conclude my talk. Okay, so as most of you know, probably all of you, basically we have, let's say, like two basic approaches in security. One is basically the classical cryptographic approaches, basically at upper layers, basically where we use algorithms, at cryptographic level. We require the key generation, distribution, and measurement, which can be quite complex, basically. And in particular, when you have a low complexity devices, basically, this can be quite a burden, basically, right? So, and in particular, when the attack is physical, it might be quite risky, basically, to rely on the complexity or on the computation complexity of the security, right? So with all this disadvantage, basically, people came up with physical layer security, and what happens there is that we use the properties of the wireless channel and its randomness, which might be multipass, noise, etc., basically. And what we claim, at least, is that it provides some low complexity approach and limited resource consumption and provides some security. The challenge here is that we are channel dependent, and the channel might limit the degrees of freedom we have in the system. And one disadvantage is if you have a strong eavesdropper channel, then the performance might degrade significantly. And then when you go to millimeter wave and terahertz systems, basically, where there is even lower randomness, basically, then this might be less effective. So the question is, how do we deal with this? So what we thought about was to use reconfigurable arrays. There are different ways, basically, of using this concept. So, or let's say, realizing this, the core idea is basically that, we want to like somehow control the wireless channel, which we so far were always assuming to be given, basically. And this, by making controllable, we have more degrees of freedom, additional degrees of freedom, which we hopefully can utilize. As mentioned, there are different approaches how to make this possible. We can use movable antennas, that we basically, have such a construction where we can move the position of the antenna. There's a concept of flexible intelligent mesosurface, basically, where you reconfigure the shape of the surface. And the concept which we have been working on a lot are so-called reconfigurable intelligent surfaces. Here, a picture of such a realization where you can control each element here individually, basically, and with this, basically, can influence the phase and the amplitude, basically, of the channel. So the approach which I'm going to focus on is this one. So essentially, it's referred to as FTA, frequency diverse array, which is something we borrowed from radar. Apparently, in the radar community, this has been used already since the 60s. But we have not found a single paper in communications using this. I mean, maybe we did a bad search, basically, but this is what happened. But we like the idea. You will see hopefully why this is a nice idea. And the basic and very simple idea is, so we are used, whenever we have like antenna arrays, that all those elements basically are using the same carrier frequency, right? But here, in FTA, that's why it's called diverse. Like each antenna element has a different carrier frequency. So this one has F0, F1, FM, and they're all different, basically. Right? So So by doing so, we have an additional degree of freedom, basically. And with this, basically, you get some, like, yeah, let's say, new degrees of freedom, which allow you like some aspects which we are used to in the near field, which we don't have in the far field, and this is why it's quite nice. Yeah, I will talk about this in detail later. Okay, so let's move on. So this concept, as I said, is in particular useful in when we consider millimeter wave and terahertz because of the limited degrees of freedom. So let's dive into details. Why is this the case? Let's say we have a conventional array, right? And we have a legitimate receiver and an eavesdropper. As long as we have such a situation that the direction of the eavesdropper is different from Bob, basically, then all is good. Basically, assuming that we are on the far field, we can do some regular beamforming, basically, in the direction of Bob, basically, and suppress any signal going to other directions. In addition to this, we can inject some noise, basically, in certain direction, basically, which makes it even more difficult for Eve to get a useful signal. And then we should be all good, right? So the challenge is basically, and this scenario 2, when the Eve is basically in the same direction as Bob. Yeah, then those approaches fail, because if we like do beamforming, then if all the signals go into the direction of Bob, then since Eve is in the same direction, independent whether I'm here or here, basically I'm always going to get some signal. I cannot inject some noise, because this is going to impact both of them, right? So this is going to fail, basically. Right? And that's why we say this conventional phase array is directionally insecure. Like from the basically angle perspective, it's basically failing here, right? So that's where basically FDA kicks in, basically, because it provides us security in both range and direction. Okay, good. So let's look at the system model first. So we are going to have a situation, very simple. So we try to keep it as simple as possible. So we have a base station, basically, with multiple antennas, and again, different frequencies, carrier frequencies here. And what we also do is we move basically the positions of the antenna. So we have movable antennas. So we have two parameters basically for each antenna: the position and the carrier frequency. Okay. And then we have this legitimate user, which is located somewhere here. So distance r and angle phi, basically. So it's here, and there are some eavesdroppers. In total, we have k eavesdroppers, which are partially located in, let's say, difficult positions, basically, right? So you see this one is in the same direction, basically, as this one. And you will also see that this is also an issue that, this eavesdropper is close by, and so on, okay? So let me see. Did I forget anything? Oh, so what we allow is that the eavesdropper actually are cooperating. So this is the worst case scenario, right? But again, the system is limited in the sense that we have only a single antenna here and single antennas here. So hopefully it can be generalized at some point. We also make the assumption that given that we are looking at millimeter wave, basically, that essentially we have only line of sight components, that makes analysis simple, basically. So the hope is that we can generalize to non-line of sight as well, and still get the same statement. So because of this, we have this very simple receive signal, basically, essentially point to point. So we have the channel here. The channel is a line of sight channel. Therefore, it's very simple. It's given by the steering vector here, A. This is an element of A, which depends on the distance and the angle, basically. So I think this is quite common, basically nothing special. The only difference is basically that you see that, this steering vector depends on F, so on the carrier frequency, and this is basically a parameter which we can play with, and it depends on X, the position of the antennas, basically. Those are the new degrees of freedom we allowed ourselves, okay? Otherwise, I think it's quite classical, nothing special. Okay, so what are the approaches we have used? We needed an objective. That's why we said, okay, let's use this one basically. Yeah, so this is basically, let's define this secrecy rate, which is nothing else than the difference between the rate towards a legitimate user minus basically the rates towards the collaborative basically eavesdroppers. Okay. Somehow this makes sense. One might come up with alternatives as well, right? Okay, so what we assume for now in our approach is basically, again, to simplify, we've just fixed the beamformer, and we said, okay, it should be okay that we use maximum ratio transmission basically. So this is this one. So that means the SNR of the legitimate user boils down to this expression. So and then when you do this, basically, then you can look at the beam pattern at basically at both the bob and the eavesdropper, and then this problem basically, so maximizing this problem basically reduces to minimizing this problem. There's nothing else basically than the leakage. This is how we can frame it. Basically, it's the leakage towards the eavesdropper. So you have the sum basically over all eavesdroppers, and then this is measuring the energy which is flowing in this direction. Okay. Again, just a suggestion. One can come up with alternatives. Okay. So I think that's all good. So let's move on. So so we came up with two algorithms, but for comparison purposes, we said, okay, we need an upper bound. And what we said is, okay, assume that basically we are able to come up with an approach basically where, let me go back, that where we are able to get rid of this completely, nothing is leaked basically, and we basically have only this expression, and then we maximize this. So this should be a legitimate upper bound, and that's what we have. So that means the results of the approaches we are getting are going to be compared with this bound, which at the beginning we thought, oh, it's going to be quite loose bound. Yeah. So okay, so let's see. So those are the general constraints we have. The positions of the antennas basically, are allowed to move only, in certain spaces basically. So of course they cannot co-locate basically, so that there needs to be a minimum distance. And then this is like the frequency per range basically we can play with, for the carrier frequency of each antenna. Okay. Good. So that's it. So the challenge is, given all this, those parameters, we have a non-convex problem. So how to solve this? So yeah, I think a very simple approach is to use simulated annealing. So that's algorithm one. So without giving further thoughts, we just said, okay, let's do this. So that's the cost function basically, and I don't think that I need to go through simulated annealing. It's just classic, nothing spectacular basically. So essentially, it gives us hopefully a solution which is something we can work with whenever we deal with those non-convex problems, right? Okay, so let's move on to algorithm 2, which is more interesting. So okay, you see something went wrong. So so the core idea of this algorithm 2 was that we said, okay, let's forget like solving this problem exactly. Let's try to solve this approximately, right? And with the hope that trying to solve this approximately, we can get the solution which is of low complexity. So maybe quadratic in complexity instead of exponential complexity. So, and hopefully, basically, when we get this result, then the bound or the gap between the upper bound and the objective, or the objective we get with our proposed algorithm is somehow bounded, right? That would be fantastic. So in order to get this, what we said, okay, we only allow like minor perturbations in terms of position and frequency. Okay, so very minor. Yeah. So and by doing this assumption, basically, like minor perturbation, there might be an expression basically which depends on the position and the frequencies, which basically can be linearized then, right? So maybe a very complicated term, and then just maybe by allowing only minor perturbation, we can linearize this. And this is what actually has been done. So we said, okay, I'm only allowed to move like minimally, basically, in the regime here, same here. And also same with the frequency, basically, I only allow small changes, right? So talking to hardware guys, basically, they told us, so like those minor perturbations are easily done, basically, and quite quickly. But if you want to, large movement, with respect to the wavelengths, basically, then you need, complicated motors and really mechanics, basically, right? So it's challenging. So they liked this, basically, right? So they said, okay, we can do this with, quite simple approaches. Okay, so that motivated us even more to go into this. So again, this is objective, and now since we allow only like minor perturbations, basically the optimization basically now depends only on those deltas, both in terms of position and frequency. Okay. Good. So, and then when you do this, basically what happens is, you see that basically in the objective, we have this function here, which is, like this exponential function. So like difficult to solve, but, since we only allow like minor perturbation, this exponential function can be very simplified by this first Taylor approximation, right? So, I mean, very basic stuff here, right? So, and then we end up having, such a term for the optimization. And now, we can, given this basic objective, basically, it's linear in the expressions here, we can find a closed form solution, basically. And this is a basic closed form solution. So very nice, actually, right? So, but the question is, I mean, is this good, right? I mean, you get a simple result, but this is good. So let's see. So this holds for both the positions and the frequencies. And this is basically already the result. Okay. So what you see here is basically, here is a conventional array. So this is basically what we basically get with the frequency diverse array, and here basically, let me see. So let's go through them one by one. So you see that in the conventional array, basically we have this directional path, and here is basically the legitimate user, and you see basically that this eavesdropper is actually getting quite a good signal, basically, right? So that means we are leaking lots of information towards this eavesdropper. I mean, here we are safe with respect to those. They are getting a bad signal. Yeah, blue means bad, but this one, is getting quite a good signal, basically, right? Now, yeah. So now when we go to basically FTA, basically, right? You see that, this is the kind of beam we are getting. So it's not a, linear beam. It's like a banded beam. You might have seen this, where, when you look at the near field, basically, beam focusing. So this is a similar picture, basically. So essentially what FTA is, basically, you're getting the benefits of near field processing in the far field, basically, right? This is what's happening. So, and now you see basically that, this eavesdropper is not an issue anymore. It's rather this one, basically, which is an issue, right? So that's basically when we, reduce ourselves to linear FTA. And now, basically, when we, keep it generalized, basically, then, so this is what we get here now with simulated annealing, basically. This is what we get now, basically. You see that, basically only within this range, basically, the signal is good, and outside of this box, basically, the signal is very bad, basically. So, okay, thank you. So, yeah, and now, if you basically only allow minor perturbations, this is what you get here. So quite, I mean, let's say similar to this one, not as good perhaps, but basically, let's say, at least in this picture here, but like almost like, as effective as this one, right? Okay, good. Good. Okay, so here's some more results. So, and this is actually nice. So we have here the upper bound. And then you see basically that, on top of this, you basically, you don't even see a difference, basically, is what we get basically by simulating and annealing. So it's essentially directly on the upper bound. Yeah. And even the minor perturbation approach, basically, which is this, dotted line here, hits actually the upper bound, basically, right? So, so that means we have been able to basically solve this complex problem. I mean, in an approximate way, quite well, basically. Yes, the gap is, negligible, and we achieve almost the upper bound. And again, for certain cases, so the proof is not complete. We have been able to show that the gap is bounded, basically. So independent of a scenario, only depending on the number of eavesdroppers and the number of antennas used. Okay, so so this is. Let me see, what was this again? So here, this is the case basically where the one eavesdropper is basically, has the same distance as Bob basically. So it's from the range perspective, the same. Then the performance drops, but still basically the upper bound and the lower bound basically agrees. And this is when we only focus on movable antennas, but don't utilize FTA, then basically the performance basically goes like this. So we are not able basically, to get good security rate, as the number of antennas goes. So this is so that essentially shows that movable antennas alone are not basically providing the benefits we have seen previously. Okay. So here's another plot basically where we have the secrecy rate as a function of K basically, and you see basically that, so here solid line is upper bound for different number of antennas at the base station, and here are basically the results we get with the two algorithms we have proposed, and you see as the number of antennas goes high, basically we are getting closer and closer to the upper bound. So just to give you final insights, so here's actually the antenna positions we are getting, basically. So this is a conventional array, and with the minor perturbation, you see basically is it purple? I think it's purple. So you see only like some minor movement of the antenna basically already provides those like substantial gains. And here in blue basically are the positions you would get if you don't restrict yourself in terms of positions. And same behavior here basically with the frequencies, basically by only allowing minor perturbation in frequencies. This is basically what we get. So very close basically to what you get in the linear FTA case. But if you make it more general, then its variance is higher. Yeah. So yeah. So in summary, so we came up with two approaches. One which tried to solve this exact problem exactly, or as good as possible with simulated annealing, and then allowing minor perturbations, and turned out that this seems to be working in particular in millimeter wave and terahertz systems. With that, I conclude my talk. Thank you.
Thank you very much for the talk. There are questions.
Okay, thank you very much. Can you go back to slide 14 where these spatial plots are?
This one?
So, yeah, exactly. So in the CND, I mean, I noticed that there are these kind of small scattered regions where you still have some kind of signal. So they kind of, is there a way of getting rid of those as well? Maybe by, wiggling the setup a little bit by additional randomization?
It might be, but at least not with the approaches we have basically. So we have used basically. So with movable antennas only, and playing around with the frequency basically, we haven't been able to do them.
Okay, so what I'm getting at is, I suspect that this pattern where you have slight signal, that depends quite delicately on the particular position. So you might still get a good signal, but I mean with a bit of a different setup. So you could just randomize over some of those. I mean, each of them would be basically just this kind of unknown to the eavesdropper. And so they could disappear. I mean, like here, it's like this. Yeah, if I know your setup, I can just position myself within one of those blobs.
Yeah.
But I think that you can shift them around quite easily with tiny variations on your. I mean, this is.
Yeah, it might be. It might work. So. Yeah, we didn't try, to be honest, but it might work. Yes. Yeah. Yeah.
So I have a direct answer to this question because the observation is really interesting. This is called acoustic. So this is the effect that you see, for example, if you are on the beach, né, and you look through the water and you see these focus points of the reflected. And of course, this is almost like random. If you move the antennas a little bit, you can create very interesting caustic patterns. But there are some results about that also available if you want to bound the maximum of these points. And so I think there is a possibility to further work on that. Yeah.
Okay. Exactly the right slide.
Okay.
But different question. Not so much interested in secrecy, but more on the beam focusing. So that's I mean, the lower two pictures, that's basically beam focusing, which we usually only see in the near field.
Yep.
So if I understand correctly, it's because you have different frequencies and you can move the antennas. Is it a single positioning of the antennas, or do you have to somehow move them more or less constantly?
No, it's you optimize it and then it stays there where it is, basically, right?
So just by being able to change slightly the position and have different frequencies, you really get a beam focusing like in the near field?
Apparently, yes.
I mean, that's cool. I mean, that's why we want huge arrays, right? Does it also work for lower frequencies, or is it limited to millimeter wave?
The challenge is that then you have multi-pass aspects, basically. Then getting closed form solution is getting ugly, basically, right? So
yeah, but the beam focusing in principle, would that work for lower frequencies, or do we then have to go back to near field? Would this multipass destroy it?
So it might work, but it's probably not as good as in this case, because there are more degrees of freedom, basically, and you have to basically deal with all the paths, basically, which are in the system. So I think it's basically trade-off. So if you're giving more antennas, basically, so which I can move, then I think it should also work with non-line of sight scenarios as well, basically, right? So, but our intention was, to get closed form solutions, basically. And if you have non-line of sight, basically, you are not able, at least so far, we have not been able to come up with closed form solutions.
Thanks, Aydin.
Yeah.
Do we have further questions? No. Okay, then thanks the speaker again.